Question number 4 is on Diels-Alder reactions, which you learned for the first exam. So the question asks, you take this and this, you react them together, and they give you a product, and what is that product? Now, let's start by identifying what is your diene and your dienophile, because every Diels-Alder reaction will involve a diene and a dienophile. At their simplest version, a diene is a carbon chain with two separate carbon-carbon double bonds, such that you have 4 carbons altogether. And then a dienophile will have 2 carbons on it that have a carbon-carbon double bond, and then typically there is some kind of electron withdrawing group on one of those 2 carbons of the dienophile. So looking at these 2 structures, this structure on the right must be your diene, because that structure has its 2 carbon-carbon double bonds. It also has an electron donating group. Single bond oxygens are typically electron donating groups. In fact, it has 2 of them. And then this then must be your dienophile, because it only has 1 carbon-carbon double bond, and it also has a pretty decent electron withdrawing group. Now, what are these OSI pH2 terbutyls and OSI Me2 terbutyls? They're things to scare you, and that's it. They put them there to make the question look weirder than it has to, but it doesn't really affect the outcome of anything you're doing. So for all you care, you could write OME and OET and pretend that's what they are, and the net result will be the same. So let's start, now that you've identified your diene and your dienophile, the next thing you always have to be on the lookout for is charges. Things that have donating groups have electrons put in, and that creates a pole where there is one end that is negative. For dienophiles, electron withdrawing groups pull electrons out, which means you create a pole where there is a positive somewhere. And you need that positive and that negative to line up when you connect your 2 carbon chains. So now let's start with the dienophile. How do we figure out where is my positive end? So there are 2 ways of doing this. One way is through drawing resonance structures, and the other way is through a little trick that I'll show after the resonance structure drawing. So if you look at a carbonyl, a C-double-bond-O, we know that always resonates one way in particular. The double bond electrons swing up to the oxygen, and you end up making O- carbon positive. So that would mean you get single bond oxygen, O-, and carbon positive. Now we want to focus on where does this charge up when it is involved with one of the 2 carbons of the double bonds we're working with. So if I look at this double bond can now resonate with that positive, and you'll end up getting a resonance structure that looks like this. And that carbon right there is the carbon that would become your positive end through resonance. And so if I draw this back the way it was originally drawn, which was this, we now know that this carbon right here is your positive end, and that must mean on your dienophile, this carbon over here is your negative end. Now if I look at this structure over here, where your positive and negative ends will be is on these 2 carbons over here, but we have to figure out which is positive, which is negative. And again, you can do it through resonance. Either this oxygen or this oxygen can resonate down, and the electrons will swing down like this. And I'm going to use the OME because these are mostly the same for both, so I don't want to mess around with those. And then this can resonate over here, and then this will push a negative charge onto this end over here. And so through that resonance, we'd end up getting this carbon to become negative. So this must be my negative end, and that must mean this end over here is positive. Now what is that trick I was talking about to make this faster than drawing resonance structures? What you can do is you can compare an oxygen to a carbon and say, well, who is more electronegative, oxygen or carbon? Oxygen is. It likes having electrons more than carbon does. Which means whenever there's an oxygen connected to a carbon, there are partial charges associated with that bond. For example here, regardless of the double bond or the single bond, this will be the same for both. We say that oxygen, because it is more electronegative than carbon, will be partially negative relative to the carbon it is attached to, so partial positive. Now if I go 1 bond further, your partial charge will just keep alternating. Meaning, if this was partial positive, this carbon over here is partial negative, which matches up with what we were saying. This is my negative end. And then if this is partial negative, this must be partial positive. So that also matches up with what I figured out through resonance. Now I'll do the same thing with this. If I look at this oxygen, and we say oxygen is partial negative relative to the carbon it's attached to, and so that carbon will become partial positive. And then this would be partial negative, partial positive, and here's partial negative. So the negative and positive ends through that method match up with what I did through the resonance as well. So that's just another fast way of doing the same thing. But for our purposes, one way or another, you now know who is positive and who is negative between your diene and your dienophile. Here's my negative and positive end here, and here's my negative and my positive end over here. Now these aren't formal charges with these structures, but these tell you how you have to line them up, because you need one positive end to line up with the negative end of another. So now I'm going to go down to this template and try to draw things in based on that. So let's start with the dienophile. The dienophile I want to have match up with this basic template where carbon 5 and 6 and the electron withdrawing group is pointing away from my diene. So my carbon 6 is on a double bond, my carbon 5 is on a double bond, and I want carbon 6 to be the one attached to my withdrawing group. So I have this, and now my withdrawing group was a C double bond O, so I'm going to draw that. And now I just have to draw out everything else in. So that carbon with the double bond O is connected to this, this, and then back to 5 in a 5-membered ring. So I have that. Now, a single bond away from 5, we have that OSI pH2 terbutyl group that was dashed. I'm just going to draw it like this. OSI pH2 TBUO, or TB, or excuse me, TBU. Okay. Double bond there, 6 and 5. Okay, so this is what my dienophile will look like in my template form. Now what about my diene? So when we get into stereochemistry, we have to worry about C and T groups, M, X, Y, and Z groups based on this template I'm giving you. But what do all those letters mean? They're a trick for figuring out if you rotate or move something around, where should it be pointing at the end. So if we look at this template right here and we focus on one of these two groups, a C or a T group off of carbon 1, cover up the other double bond and now compare, let's start with the T group. Compare that T group to its position relative across the double bond from 2 and 3, the 2 and 3 bond. Well, if I look at that, that looks like a trans double bond, right? One way and then the other way. And that's why it's a T group. So I can do that here. Cover up one double bond, we have an OME that we have to think about. So that OME is sticking up and then hits a double bond, and then the bond between 2 and 3 is pointing in the opposite direction. So this OME is also a T group. Now, we said that carbon 6 is our negative end, carbon 5 is our positive end. We want this carbon, this positive end, to line up with this end over here, this negative end. So I'm going to say that carbon 1 is my positive end, and that means I want 1, 2, 3, and 4. So I need that to line up. I said it was a T group, which means it's going to be pointing out like that, because I want it to look trans when I draw it in with this double bond. Okay? Now, what else do I have? Based on this numbering, I also have an OSI Me2TBO. I said that weird. And that's coming off of 3, so I'm going to write OSI Me2, and at that point I don't really want to write anymore. TBU. Okay, so these are my two pieces. These are my positive and my negative ends, and they're lined up with each other in the right way. So now I can start connecting connecting them to each other. Now, how am I going to do that? Well, I've lined them up, so I don't really need to write the positive and negative ends anymore, so I'm going to erase those just for clarity's sake. Now, how you do it is there's always 3 arrows to this mechanism. Let's start with the easy one. One of the double bonds between 1 and 2 is going to now move its electrons to the bond between 2 and 3. This shows that this double bond is breaking and a new double bond is forming between 2 and 3, which you should expect. There will always be one double bond in the product of your Diels-Alder reaction. The next arrow shows that the bond between 3 and 4 is going out to make a bond between 4 and 5. Since there's no bond between 4 and 5 right now, you're drawing to a no bond essentially. This is a no bond, a 0 bond, but this arrow ending there implies that you're making a new single bond. And you're going to do the same thing for the double bond between 5 and 6. That goes out to the bond between 1 and 6, and now you're making a new single bond from where there was no bond. Okay? So now I'm going to use these arrows to justify what I'm supposed to get. This was a double bond, but the arrow starts from that, so now it's a single bond. This was a no bond, but it has an arrow going to it, so it's a single bond now. This double bond has an arrow starting from that, so it must become a single bond. And those electrons based on the arrow are being used to create a new bond between 6 and 1. finally, the last arrow between 1 and 2 starts from a double bond, so that double bond must become a single bond now. And that arrow ends at the bond between 2 and 3, so a double bond must form between 2 and 3. So this is what my product should look like before I worry about stereochemistry. And now to figure out the stereochemistry, we again turn to this template here. I accidentally erased it, and now I realize that, but the rule that you have to know is the endo versus the exo rule. Now this question neither specified endo or exo. What it did say was just find the product. So if they don't specify endo versus exo rule, just assume it's the endo rule. And what the endo rule states is that your T, your Z, and your EWG groups will have the same stereochemistry as each other, same stereo, but will be opposite your C, X, and Y groups. So now let's go back to this structure these structures that we started with. This was O and E. Okay. So we said before that carbon 1 is a T group, meaning that it is trans relative to the double bond and the bond between 2 and 3. And we said that T groups must be the same stereochemistry as my withdrawing group. So I can choose wedge or dash and base it off of that. I'm going to say, let's make my withdrawing group dashed. And that just means I have to base everything off of that statement now. So if this bond to the withdrawing group is dashed, this OME group, which we said was a T group, must also be dashed. And then the bond coming off of 5, it's going in the same direction as the bond. So the bonds on 5 and 6 are going out like this. So this looks like a cis bond. If this is my withdrawing group and this is on the same side as my withdrawing group, that means it's a Z group. And we said Z groups also have the same stereochemistry. So that would mean I'm drawing a dashed line here. Now this obviously looks weird because you have two dashed lines to the same carbon. That doesn't make sense. And it's not going to match up with anything on your answer key. So this points out something that is probably incorrect. There's another way to think about this. Look at 5 and 6 for a second. There's something else on those two carbons that we didn't draw out. Hydrogens. Both of these have hydrogens, and they are pointing in the opposite direction of the withdrawing group on 5 and 6, which means they are comparable. If this is my withdrawing group over here, they are comparable to your X and your Y groups. And we said X and Y will have opposite stereochemistry to your withdrawing group. If the withdrawing group is supposed to be dashed, and your Z group is supposed to be dashed, that means your X and Y would be wedged. So two wedged hydrogens. This is another way of drawing the same thing, where they draw the extra ring planar, but then they draw the hydrogens in with the according, with the proper stereochemistry based on the rules in this template that I'm giving you. Now, again, if you look at your answer key, this still isn't an answer on the list because for some reason they chose to not emphasize the stereochemistry of your OME group. They just left the OME planar in every answer choice. If this question was 100% correct, that OME would have to have opposite stereochemistry of these two hydrogens. But as far as the answer choices are concerned, as long as you saw that the hydrogens have to have the same stereochemistry, you can get the right answer. So if we look at the answer choices, that automatically rules out choice B, C, D. Yes, so choice B, C, and D, which leaves A, E, and F. But then it comes down to, are my OSI Me2 TBU and my OSI PH2 TBU groups in the right spot? And if you look at it from that perspective, only choice E has everything in the right spot with your two hydrogen groups having the same stereochemistry as each other. Remember, you always make an enantiomer. While I chose to say the withdrawing group is dashed and therefore the hydrogens are wedged, there's the enantiomer which says the opposite. The withdrawing group is the one that's wedged and the hydrogens are both dashed, which is what you see in choice E. So this was kind of an ugly Diels-Alder problem, and I think there's another one in this somewhere, but this is probably one of the ugliest Diels-Alder you'll work with.